Today we're going to continue with arithmetic sequences, and we're going to learn something called the explicit and recursive formulas for arithmetic sequences. We already know what a sequence is at this point, and we know how to find the first several terms using the common difference and repeating the pattern over and over again. So we already know how to find, say, the first and the third and the fifth term in the sequence. But what if I wanted to find the 100th term of the sequence, or even the 2000th term of a sequence? That definitely would not be very convenient because I would not want to take the time to write out all of those terms. Very time consuming. Well, there is a better way. Let's start with a sequence 3, 5, 7, 9, 11. We can tell that the sequence starts at 3, and our common difference that's being added each time I go from one term to the next is 2. We're going to focus for just a second on what's being added to the first term in order to get to the second, third, fourth, fifth term, and so on. So let's take a look. All right, to start off with, we know that our starting value is 3. To get from 3 to the second term, which is 5, I add 2. To get from the first term to the third term, from 3 to 7, we add 4. To get from 3 to 9, we add 6. From 3 to 11, we add 8. And to get from 3 to 13, we add 10. And this pattern itself, like I could do this all day, right? Because this is an infinite sequence. But I want you to look for just a second at the numbers that we added. Isn't that a pattern in and of itself? 2, 4, 6, 8, 10? How much do you think we'd have to add to 3 to get to the next term in our sequence? Wouldn't that be 12? Then 14, then 16, then 18, and like I said, we could do that forever. I'm even going to say that from 3 to itself, I would add 0. That's going to help us in our pattern as well. Okay, let's focus on the numbers in white. Like I said, there's a pattern in everything having to do with a sequence. To get from the first term to the second term, I had to add 1 multiple of 2. To get from 3 to 7, from the first term to the third term, I added 2 multiples of 2. To get to the fourth term, I added 3 multiples of 2. To the fifth term, I added 4 multiples of 2. To the sixth term, I added 5 multiples of 2. Well, isn't 2 our common difference, our original common difference? Weren't we adding 2 to get from 3 to 5 and from 5 to 7? Yeah, 2 was our common difference. And like I said, to get to the second term, didn't I have to multiply 1 multiple of our common difference? To get to my third term, didn't I have to multiply 2 of our common difference, or add, 2 of our common difference? And then to the fourth term, I added 3 of the common difference. Can you kind of see that there's a pattern there as well? I'm even going to say that to get to the first term, I added none of our common difference. So can you see that the first term, or the term number, and the number of common differences I had to add is decreased by 1, right? To get to the third term, I had to add 2 of the common difference. To the fourth term, I had to add 3 of the common difference. Fifth term, I had to add 4 of the common difference. So let's say to get to the 10th term, wouldn't I have to add 9 of those common differences? That's supposed to be a 9. So we kind of repeated over and over multiples of 2, right? Which was our common difference, of course. So we took our common difference and we had to multiply by 1 less than the term number, right? Well, n, if you remember back to our previous discussion on sequences, n refers to the term number. So didn't I take the common difference and multiply it to 1 less than the term number? Absolutely. And what did we always have to add that to get the actual term itself? Like, what did I add 10 to get 13? Well, it all came down to everything was added to that starting value or initial value, a sub 1. And that actually gives me any term in the sequence, a sub n referring to any term in the sequence. So this is actually called the explicit formula for arithmetic sequences. We're going to say, and sorry about the handwriting here, the software I use doesn't allow me to write very well, but a sub n referring to any term in the sequence, we take our initial term and add it to our common difference multiplied by 1 less than the term number. This is our explicit formula for arithmetic sequences. So let's say that I wanted to take the sequence I had before and find the 100th term of that sequence. Well, remember, in this case, a sub 1, or in that sequence, a sub 1 was 3, and our common difference was 2. So I use these values and plug them in. Oh, and I want to find the 100th term, so that's n. I'm going to include that too. I'm going to plug those values into this formula and find my 100th term. So I want to find a sub 100, which is the 100th term in the sequence. I take the initial value, 3, and add it to my common difference, multiplying my common difference by 1 less than the term number itself, 99. And then in order to do that, we're going to pull up a calculator. An order of operations, of course, says that multiplication needs to come before addition. So I'm going to do the 2 times 99 first, then add it to 3. And I get a total of 201. So let's write that in. That all equals 201. Well, 201, we just solved our problem, would be the 100th term or number in that sequence on the previous page. And I did it with not a whole lot of effort, right? I had to write the equation, and then of course I had to use my calculator to multiply it out. Let's try that on a different sequence. First of all, we want to write the explicit formula for this sequence. Remember, we need to know the important parts of this sequence. Our initial term is 4. What's our common difference this time? Common difference is 6. That's what we're adding to get from one term to the next. And then n in this case, well, let's just write the general explicit formula first. So to find any term in the sequence, we take the initial term, add it to the common difference multiplied by 1 less than the term number. So if I want to find a sub 85, the 85th term in the sequence, instead of writing out all 85 terms, I take 4 added to 6 times 1 less than that term number, 84. And then again, I can use my calculator to solve. Do the multiplication first, 6 times 84, then add to 4, I get 508. And that would end up being the 85th term in my sequence. One more. Because on this one, our common difference is negative. And you always need to be a little careful when you have a negative common difference. Of course, we need our initial term, which is 4. Our common difference, instead of saying we're subtracting 4, remember we say we add negative 4. And then we have enough information to write our general explicit formula. A sub n equals 4, our initial term. I can say plus negative 4, or I can say minus 4, either way is fine, times 1 less than our term number. If I want to find the 60th term in the sequence, then 4 minus 4 times 1 less than the term number at this time would be 59. So when I bring out that calculator, let me clear off what I had before. I'm going to do 4 times 59. I could do negative 4 times 59, not a big deal. There's lots of ways to plug this in. You just have to keep track of what you're doing. I'm going to have 4 minus 236, which is going to be negative 232. And that would be the 60th term in that particular sequence. Now we're going to quickly talk about recursive formulas. We know now what the explicit formula for arithmetic sequences looks like, and remember that's used for finding terms that are too far off for you to write down all the terms of the sequence that you need. But there's another formula that has to do with sequences called the recursive formula, where the explicit formula makes it easy to find a certain term in a sequence, great for finding terms that are far off in your sequence. A recursive formula is notation based only. That means that it's not really helpful in finding terms of your sequence. It helps you write the sequence down and find out the pattern, but it doesn't actually help you solve for anything. So, there's 2 parts to a recursive formula. The information that the recursive formula gives us is the initial term, because we always have to have a starting value, and a formula that says to find the next term in the sequence, or any term in the sequence, you take a sub n minus 1. Remember, if n is the term number, n minus 1 must be the term before. So to find any term in the sequence, you're going to take the term before and simply add the common difference. So again, recursive formula requires 2 parts: where it starts and what the pattern is. So let's just take a quick look. For this particular sequence, 7, negative 2, negative 11, negative 20, and so on, we have an initial term of 7 and a common difference of negative 9. So our explicit formula would be a sub n equals 7 plus negative 9 times n minus 1. Our recursive formula says our initial term equals 7. So a sub 1 equals 7, comma, a sub n equals a sub n minus 1. To get any term, you take the term before and subtract 9, or add negative 9. I could write it either way. Now here's my question. If I only needed to find the 6th term, which formula would be most important to me? Well, if I only need to find the 6th term, I could just write out the pattern recursively. That's what it's called when you simply write or continue the pattern, right? I already have the first 4 terms. To continue on to the 6th term, I just continue the pattern, and I'd get negative 29, and then I'd have negative 38. And that would be the 6th term in my sequence. 1, 2, 3, 4, 5, 6. But to find the 201st term, I definitely don't want to write out the sequence recursively. I'd rather use the explicit formula. So I would have a sub 201, right? Go through all of this. 7 plus negative 9 times 200. Negative 9 times 200 gives me negative 1800. Adding that to 7 gives me negative 1793. And that would be the 201st term in my sequence. Let me show you why it's important, or why the two parts of a recursive formula are so important. My first sequence, the main part of my recursive formula, a sub n, to get any term in the sequence, I take the term before, and what's my common difference? We're adding 3 to each term to get to the next. Well, in my second sequence, I have a sub n. To get any term in this sequence, I take the term before, and don't I add 3 here as well? Of course, right? But both recursive formulas look the same. So what makes the difference between the first sequence and the second sequence? The initial term. This first sequence has an initial term of 2. It starts at 2. And then we add 3 each time. The second one starts at 7. And we add 3 each time to get from one term to the next. That's why both parts of the recursive formula are so very important. Don't forget to include them both. So really quickly, if I want to write a recursive formula for the following sequence, what parts need to be included? We need to include the initial term, and that a sub n will always equal a sub n minus 1, the term before, and in this case, our common difference is 6. All right, I think that's enough for today. Don't forget to know the difference between explicit and recursive formulas. I hope you have a fantastic day, and I'll see you next time.